What if everything you've ever learned about space is only part of the story? What if one of the most terrifying sounds ever released by NASA did not come from a science fiction movie, but from a real object nearly 250 million light-years away? And what if that haunting, low, rumbling tone wasn't the voice of a black hole at all, but the heartbeat of an entire galaxy cluster? For generations, we have been taught a simple scientific fact. There is no sound in space. It is one of the first lessons we learn about the universe. Astronauts cannot hear explosions outside their spacecraft. Stars do not roar. Planets do not echo. Even if two massive asteroids collided in the emptiness between planets, no one floating nearby would hear the impact with their own ears. Hollywood often ignores this reality, filling epic space battles with thunderous explosions and roaring engines. Real space is different. Real space is silent. Or at least, that's what we have always believed. Then NASA released something that stunned millions of people around the world. A deep, unsettling sound. Slow, ancient, almost impossible to describe. It spread rapidly across social media, news websites, classrooms, podcasts, and television programs. Some people called it the scream of a black hole. Others described it as the sound of the universe mourning itself. Many admitted they felt uncomfortable the moment they pressed play. The recording didn't resemble music. It didn't resemble machinery. It sounded distant, cold, and strangely alive. Within days, millions of listeners were asking the same question. How can a black hole make a sound if sound cannot travel through space? It seemed like a contradiction. Either everything we knew about physics was wrong, or NASA had discovered something extraordinary. As it turns out, the truth is even more fascinating. Before we continue our journey into one of the strangest discoveries in modern astronomy, if you enjoy deep space documentaries that explore the greatest mysteries of the universe, consider subscribing to the channel. It helps us create more long-form scientific documentaries like this one. And while you're here, leave a comment telling us where in the world you're watching from. It's always incredible to see this community of curious minds stretching across different countries and continents, all exploring the universe together. Now, let's begin with the mystery itself. The statement that there is no sound in space is not a myth. It is scientifically correct. Sound is a mechanical wave. Unlike light, which can travel through empty space as electromagnetic radiation, sound depends on something physical to carry it. Air, water, steel, glass, even solid rock. Every sound you've ever heard has traveled through countless tiny collisions between particles. When someone speaks, vibrating vocal cords push against nearby air molecules. Those molecules bump into neighboring molecules. The disturbance spreads outward until it reaches your ears. Your brain then transforms those vibrations into voices, music, laughter, or thunder. Without particles, there is nothing to vibrate. Without vibrations, there is no sound. This is exactly why astronauts communicating during a spacewalk rely entirely on radio signals. If two astronauts floated only a few meters apart and one removed the radio, shouting would accomplish absolutely nothing. Their voices would never cross the vacuum separating them. The silence would be complete. Our own solar system illustrates this perfectly. Although the sun constantly erupts with gigantic explosions, solar flares, and violent magnetic storms, releasing unimaginable amounts of energy, almost all of the space between the planets is astonishingly empty. The remaining particles are so incredibly sparse that ordinary sound waves simply cannot travel through them. From Earth, the sun appears blazing and energetic. Yet if you could somehow stand nearby in open space, protected from its impossible heat, you would hear nothing. No roaring fire, no crackling plasma, only silence. That silence has shaped humanity's image of the cosmos for generations. Space became synonymous with emptiness, an endless silent void stretching beyond imagination. So when NASA announced that scientists had transformed data from a distant black hole into something we could actually hear, confusion spread almost immediately. Headlines around the world used dramatic language. NASA records the sound of a black hole, the scariest sound ever captured. The universe has a voice. Many readers understandably assumed that NASA had somehow placed a microphone near a black hole. Of course, no microphone could survive such an environment, nor could any spacecraft currently travel there. Something entirely different had happened. The object at the center of this story is not located inside our own galaxy. It lies within the Perseus Galaxy Cluster, one of the most massive structures in the nearby universe. Roughly 250 million light-years from Earth, thousands of galaxies drift together inside an enormous cloud of extremely hot gas known as the intracluster medium. Unlike the near-perfect vacuum surrounding Earth, this environment is surprisingly different. It is still unimaginably thin compared with Earth's atmosphere. Yet across millions of light-years, enough particles exist for enormous pressure waves to travel through the gas. Not ordinary sounds that human ears could detect, but real physical waves moving through matter. At the center of the Perseus cluster sits a supermassive black hole. Far from being quiet, this cosmic giant constantly releases astonishing amounts of energy. As matter spirals inward, some of that energy is redirected outward in colossal jets traveling at nearly the speed of light. Those jets inflate gigantic bubbles inside the surrounding hot gas. Just as a stone dropped into a pond creates ripples across the water, these expanding bubbles generate enormous pressure waves that slowly spread throughout the galaxy cluster. The process unfolds over millions of years. The waves are unimaginably slow. Their frequency is so incredibly low that no human ear could ever detect them naturally. In fact, one complete oscillation takes thousands of years. Imagine trying to listen to a musical note so deep that its wavelength stretches across enormous regions of intergalactic space. Such a sound lies far beyond the limits of human hearing. Yet mathematically, it is still a wave, and waves can be measured. This is where NASA made its remarkable contribution. Scientists did not record the sound using microphones. Instead, space telescopes, particularly the Chandra X-ray Observatory, observed subtle ripples in the hot gas surrounding the black hole. These ripples revealed pressure variations moving through the cluster. Researchers then converted those measured frequencies into audible sound by increasing their pitch by many orders of magnitude. This scientific process is known as sonification. Nothing was invented. Nothing fictional was added. The underlying data came directly from astronomical observations. What changed was only the scale. Just as invisible infrared light can be translated into visible colors, or radio waves can become images, pressure waves too slow for human hearing can be transformed into sound without changing the physical information they contain. In other words, NASA did not discover that black holes suddenly produce audible noise. NASA discovered a way to let human senses experience data that had always been beyond our biological limits. That distinction is incredibly important. The famous recording is not the literal sound a microphone would capture. It is something arguably more valuable. It is science translating the language of the universe into a form our brains can understand. And once you realize that, the recording becomes even more extraordinary. Because those haunting vibrations are not merely eerie audio. They are evidence that a black hole is continuously interacting with an entire galaxy cluster, hundreds of millions of light years away. Every pulse carries information. Every ripple tells a story. Every oscillation reveals something about gravity, plasma, energy, and the invisible structure of one of the largest environments in the universe. The mystery, however, is only beginning. If the recording is based on genuine pressure waves, what exactly creates those waves? How can a black hole, an object famous for trapping everything that falls into it, produced disturbances powerful enough to ripple across millions of light years. And what does that reveal about the hidden engines shaping entire galaxies? To answer those questions, we must first travel to one of the largest known structures in the nearby universe, the immense Perseus Galaxy Cluster, where the silence of space is not as silent as it first appears. The haunting sound released by NASA has been described in countless ways. A ghostly moan, a cosmic growl, the voice of a sleeping giant, even the scream of a black hole. But before we can understand what we are hearing, we must first understand what NASA actually observed. Because the remarkable truth is this: NASA never pointed a microphone toward space. There were no giant speakers floating between galaxies. No spacecraft carrying recording equipment close enough to capture a black hole's roar. In fact, if you place the world's most sensitive microphone beside the Perseus Galaxy Cluster, it would record absolutely nothing your ears could hear. So where did the famous sound come from? The answer begins with one of the most powerful astronomical observatories ever built. High above Earth's atmosphere, orbiting nearly 17,000 kilometers per hour, is NASA's Chandra X-ray Observatory. Launched aboard the Space Shuttle Columbia in July 1999, Chandra was designed for a mission unlike any optical telescope. Instead of observing visible light, Chandra studies the universe through X-rays, the highest energy form of electromagnetic radiation commonly produced by some of the most violent events in the cosmos. To human eyes, the universe appears calm. Stars gently twinkle, galaxies glow softly against the darkness. But in X-rays, the universe becomes astonishingly energetic. Exploding stars illuminate enormous clouds of superheated gas. Colliding galaxy clusters release unimaginable amounts of energy. Matter falling toward black holes shines brighter than entire galaxies. Without X-ray telescopes like Chandra, much of this invisible universe would remain completely hidden. That is precisely why Perseus became one of Chandra's most important targets. Located approximately 250 million light-years away, the Perseus Galaxy Cluster is among the brightest X-ray sources in the sky. Not because its stars are unusually luminous, but because the vast space between its galaxies is filled with an ocean of plasma heated to tens of millions of degrees. This plasma emits intense X-rays continuously. To Chandra, Perseus does not appear as empty darkness. It resembles an enormous glowing cloud surrounding thousands of galaxies. And at its very center, something extraordinary is happening. The giant elliptical galaxy, NGC 1275, dominates the heart of the cluster. Hidden within its core lies a supermassive black hole containing hundreds of millions of times the mass of our Sun. Despite its name, a black hole is rarely quiet. As enormous quantities of gas spiral inward, gravity converts their motion into tremendous amounts of energy. Temperatures rise into the millions of degrees. Magnetic fields become violently twisted. Some material disappears forever beyond the event horizon. But not all of it. Before crossing that invisible boundary, part of the infalling matter is redirected outward in narrow jets traveling at nearly the speed of light. These relativistic jets shoot far beyond the galaxy itself. As they plow into the surrounding plasma, they push enormous volumes of hot gas aside. Imagine blowing air into a balloon beneath the surface of a swimming pool. The expanding balloon forces water outward, creating ripples that travel across the pool. Something remarkably similar occurs in the Perseus cluster, except instead of water, the surrounding medium is plasma. Instead of a balloon, the expanding cavities are each larger than entire galaxies. Astronomers call these enormous structures plasma bubbles. Chandra's X-ray images revealed them as dark cavities embedded within the brilliant glow of the surrounding hot gas. At first, scientists were puzzled. Why would there be enormous empty-looking holes inside one of the brightest X-ray sources in the universe? The answer slowly became clear. These weren't empty spaces. They were giant bubbles inflated by the black hole's powerful jets. As each bubble expanded, it displaced the surrounding plasma. That expansion generated enormous pressure waves moving outward through the cluster. These waves are surprisingly similar to sound waves traveling through Earth's atmosphere. Both consist of alternating regions of compression and rarefaction. Both transport energy through matter. Both obey the same fundamental principles of wave physics. The difference lies almost entirely in scale. On Earth, a sound wave may travel a few meters in fractions of a second. Inside the Perseus cluster, these pressure waves travel across hundreds of thousands of light years over millions of years. The rhythm is unimaginably slow. One oscillation corresponds to a frequency nearly 57 octaves below middle C on a piano. To appreciate just how low that is, consider the deepest note a human can hear. Most people perceive sounds only down to about 20 hertz, meaning 20 vibrations every second. The pressure waves in Perseus vibrate roughly once every tens of thousands of years. Their frequency is approximately one vibration every 10 million years. No human ear could ever detect something so incredibly slow. Even if you somehow survived inside the cluster, your lifetime would pass before a single complete wave finished its cycle. Yet physics does not care whether humans can hear it. A wave remains a wave regardless of our biological limitations. This realization inspired an ingenious idea. What if scientists could preserve the pattern of those waves while shifting them into the range of human hearing? The concept is surprisingly familiar. Think about a piano. Move every note upward by several octaves, and the melody remains recognizable, even though every frequency has changed. Similarly, astronomers increased the frequencies measured within the Perseus cluster by approximately 57 to 58 octaves, or millions of billions of times. The relationships between the waves remained intact. Only their pitch changed. The result was the now famous recording that captured the world's imagination. What listeners hear is therefore not an invented soundtrack. It is not a composer attempting to imagine what a black hole might sound like. It is the genuine mathematical structure of real astronomical data translated into an audible form. This process is known as sonification. Sonification has become an increasingly valuable scientific tool across many disciplines. Weather researchers convert climate patterns into sound. Medical specialists transform heartbeat data into audio. Seismologists listen to earthquake vibrations. Even stock market analysts occasionally convert financial data into musical patterns to detect hidden trends. The goal is not entertainment, it is perception. The human brain often recognizes subtle patterns through hearing that might otherwise remain hidden inside graphs or spreadsheets. Astronomy has embraced this approach because the universe produces extraordinary amounts of information that lie beyond human senses. Our eyes perceive only a tiny fraction of electromagnetic radiation. Our ears detect only a narrow band of sound frequencies. Our bodies cannot directly experience X-rays, radio waves, gamma rays, gravitational waves, or magnetic fields. Science continually develops new ways to translate these invisible phenomena into forms we can understand. False color images are one example. When astronomers publish breathtaking photographs of distant nebulae, the colors often represent wavelengths invisible to human vision. No one accuses those images of being fake. They are scientifically meaningful translations. The Perseus sound follows exactly the same philosophy. Instead of converting invisible wavelengths into colors, NASA converted inaudible pressure oscillations into sound. The information remained authentic, only the sensory language changed. However, this process has important limitations. Sonification is not equivalent to placing a microphone in space. It cannot perfectly recreate what an imaginary observer might hear. Choices must be made during data processing. Scientists decide how rapidly to scale frequencies, how to filter background noise, and how to represent multiple signals simultaneously. Different processing methods can produce slightly different listening experiences while remaining scientifically accurate. This does not reduce the value of the data. It simply reminds us that every translation, from numbers to sound, or from X-rays to images, involves interpretation. The scientific measurements remain objective. The presentation is designed for human understanding. That distinction matters, because the famous recording should never be interpreted as proof that black holes literally roar across the universe like monsters from science fiction. Instead, it demonstrates something arguably far more remarkable. The universe contains physical processes occurring on scales so vast that our senses alone could never perceive them. Through technology, mathematics, and careful observation, humanity has learned to extend those senses far beyond their natural limits. For centuries, astronomy relied almost entirely on visible light. Today, scientists explore the cosmos using radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays, neutrinos, gravitational waves, and now even carefully translated sound. Each new method reveals another hidden layer of reality. The Perseus recording is not merely an eerie curiosity. It represents a new way of experiencing the universe, not because space has suddenly become noisy, but because human perception has grown wider. Yet one mystery remains. If these immense pressure waves truly exist, what gives them enough energy to travel through an entire galaxy cluster? How can a single supermassive black hole influence an environment stretching across millions of light years? To answer that question, we must journey deeper into the Perseus cluster itself, where an invisible ocean of superheated plasma fills the darkness, and where one of the universe's largest cosmic engines quietly reshapes an entire region of space. Before we can understand why a black hole appears to produce sound, we must first travel to one of the largest structures in the nearby universe. Not a planet, not a star, not even a single galaxy, but an entire galaxy cluster. The famous recording released by NASA did not come from an isolated black hole drifting through empty space. It originated inside the Perseus Galaxy Cluster, a colossal cosmic metropolis located approximately 250 million light-years from Earth. To appreciate that distance, imagine traveling at the speed of light, the fastest speed permitted by the laws of physics. Even then, your journey would take 250 million years. The light reaching our telescopes today began its journey long before the first dinosaurs appeared on Earth. What we observe is not the Perseus cluster as it exists now. It is a portrait from Earth's unimaginably distant past. Yet even from that staggering distance, Perseus has become one of the most important laboratories for understanding how black holes shape the universe. At first glance, a galaxy cluster may seem like a simple collection of galaxies gathered by gravity. That description is technically correct, but dramatically incomplete. The Perseus cluster contains well over 1,000 galaxies, each holding billions or even hundreds of billions of stars. Spiral galaxies, elliptical galaxies, dwarf galaxies, ancient stellar systems that have been interacting for billions of years. Together, they form a gravitational structure spanning more than 11 million light-years across. If our own Milky Way were placed inside Perseus, it would appear as just one ordinary member among many. The scale is almost impossible to comprehend. If the Milky Way were reduced to the size of a single grain of sand, the Perseus cluster would still resemble an enormous beach stretching far beyond the horizon. Yet, despite containing thousands of galaxies, they account for only a small fraction of the cluster's visible matter. The real giant hiding inside Perseus is something almost invisible: an enormous ocean of incredibly hot gas. This gas fills nearly every space between the galaxies. Unlike the colorful clouds found inside nebulae, the gas in Perseus exists as plasma, often called the fourth state of matter. At temperatures reaching 30 to 100 million degrees Celsius, atoms cannot remain intact. Electrons are stripped away from their nuclei, creating an electrically charged sea of particles. This plasma is so hot that it shines brightly in X-rays. That is precisely why NASA's Chandra X-ray Observatory can see it so clearly. If human eyes were sensitive to X-rays instead of visible light, the Perseus cluster would not appear mostly dark. It would glow like an enormous cosmic furnace. For many people, this raises an obvious question. If space is supposed to be a vacuum, why is there so much gas? The answer lies in understanding what scientists really mean when they describe space as empty. A vacuum does not necessarily mean absolute nothingness. Instead, it describes a region containing very few particles. Even the emptiest regions between galaxies contain stray atoms, energetic particles, magnetic fields, and invisible radiation. Absolute emptiness may not exist anywhere in the observable universe. The space surrounding Earth illustrates this perfectly. Although we often describe outer space as a vacuum, millions of particles from the solar wind continuously stream through the solar system. Cosmic rays race across interstellar space. Hydrogen atoms drift between the stars. The difference is density. Near Earth, these particles are extraordinarily sparse, too sparse to efficiently carry sound. The Perseus cluster is different. It is still astonishingly empty compared with Earth's atmosphere. But compared with ordinary interstellar space, it is surprisingly crowded. Imagine removing almost every molecule from Earth's atmosphere until only a tiny handful remained inside a room. That room would still be vastly denser than most regions of space. Yet on cosmic scales extending millions of light years, even such an incredibly thin gas becomes significant. Scientists estimate that the plasma within Perseus contains only a few particles per cubic centimeter. That sounds almost unbelievably empty. Earth's atmosphere near sea level contains roughly 25 quintillion molecules in the same volume. In other words, the air surrounding you right now is trillions upon trillions of times denser than the plasma filling the Perseus cluster. If you could somehow stand inside that plasma without protection, you would not feel wind. You would not struggle to breathe. There would be almost nothing to inhale at all. By every everyday standard, it would seem completely empty. Yet nature does not operate according to human intuition. Even this extraordinarily thin plasma extends across millions of light years. When multiplied by such unimaginable distances, it contains an enormous total mass. More importantly, it provides exactly what sound-like pressure waves require. Particles. Not many, but enough. Imagine dropping a pebble into a still lake. The disturbance spreads outward because water molecules push against neighboring molecules. Now imagine replacing that lake with an immense ocean, whose water is spread so thin that individual droplets are separated by enormous distances. The ripples would travel much more slowly and much less efficiently. But if the droplets still interacted, waves could still exist. The Perseus cluster behaves in much the same way. The plasma is unimaginably diffuse, yet neighboring particles still exchange energy through collisions and electromagnetic interactions. Pressure disturbances propagate throughout this gigantic medium. Not rapidly, not loudly, but continuously. This is why scientists often describe the waves surrounding the Perseus black hole as pressure waves rather than ordinary sound. The underlying physics is fundamentally similar: compression, expansion, energy moving through matter. The scale, however, is unlike anything humans experience on Earth. Consider the speed of sound. At sea level, sound travels through air at approximately 343 meters per second. Inside water, it moves more than 4 times faster. Within steel, even faster still. In the superheated plasma of Perseus, the speed of sound reaches approximately 1,000 to 15,500 kilometers per second. That is fast enough to travel from New York to Los Angeles in only a few seconds. Yet, despite this astonishing speed, the waves themselves remain incredibly slow. Why? Because their wavelength is unimaginably enormous. Picture ocean swells stretching not for meters, not for kilometers, but across hundreds of thousands of light years. Each crest and trough encompasses regions larger than entire galaxies. One complete oscillation may require millions of years. No creature evolving on Earth could naturally perceive such rhythms. To us, they would appear almost perfectly still. This remarkable environment makes Perseus extraordinarily unusual. Most regions of the universe cannot support pressure waves over such immense distances. Inside our own solar system, particles are simply too sparse. Interstellar space between stars is usually too empty as well. Even many galaxy clusters lack the combination of hot plasma, enormous mass, and energetic central black hole required to generate clearly observable wave patterns. Perseus possesses all of these ingredients simultaneously. A vast reservoir of plasma, a supermassive black hole at its center, continuous energy injection through relativistic jets, and millions of years for those disturbances to propagate outward. The result is one of the largest naturally occurring wave phenomena ever observed. These waves accomplish far more than simply creating fascinating data. They help regulate the entire life cycle of the cluster. Without them, the hot plasma would gradually cool. As it cooled, enormous quantities of gas would collapse toward the central galaxy, forming stars at extraordinary rates. Astronomers once expected precisely this outcome. Yet observations revealed something very different. The gas remained unexpectedly hot. Star formation occurred much more slowly than theoretical models predicted. For decades, this discrepancy puzzled scientists. The answer appears to lie within the black hole itself. Each time the central black hole launches energetic jets, enormous bubbles expand through the plasma. Those bubbles inject energy back into the surrounding gas. The pressure waves carry that energy outward like ripples spreading across a pond. Instead of allowing the cluster to cool continuously, the black hole repeatedly reheats its environment. Remarkably, the object most famous for swallowing matter also acts as a cosmic thermostat. Rather than merely destroying its surroundings, it helps maintain the delicate balance governing an entire galaxy cluster. This process is known as AGN feedback, and it has become one of the most important discoveries in modern astrophysics. It reveals that supermassive black holes are not passive consumers hidden inside galaxies. They are active architects influencing structures millions of light years across. Every ripple detected in Perseus tells part of that story. Every pressure wave records another cycle in the long conversation between gravity and plasma. Every oscillation preserves evidence of an invisible engine operating across cosmic time. Without the surrounding ocean of hot gas, none of those waves would exist. Without those waves, NASA would never have produced the now famous recording. And without the extraordinary environment of the Perseus cluster, humanity might never have realized that even one of the quietest places in the universe possesses rhythms of its own. Yet one profound mystery still remains. If the surrounding plasma merely carries the waves, what actually creates them? How can a black hole, an object from which not even light can escape, produce disturbances powerful enough to shake an entire galaxy cluster spanning millions of light years? The answer lies not inside the event horizon, but in the violent region just beyond it, where gravity, magnetic fields, and blazing plasma combine to create one of the universe's most powerful engines. From a distance, the heart of the Perseus Galaxy Cluster appears almost peaceful. Thousands of galaxies drift silently through a glowing ocean of superheated plasma. Nothing about this immense structure suggests violence. Nothing hints at the extraordinary engine hidden deep within its center. Yet appearances can be profoundly deceptive. At the core of the giant elliptical galaxy NGC 1275 lies one of the universe's most powerful natural machines, a supermassive black hole whose influence extends far beyond the stars surrounding it. Unlike the stellar black holes formed when massive stars collapse, this cosmic giant belongs to an entirely different class. It contains hundreds of millions, possibly approaching a billion, times the mass of our Sun. If our solar system were placed beside it, the black hole itself would still remain invisible. Its event horizon would swallow light, making it impossible to observe directly. And yet, its presence is unmistakable. Not because we can see the black hole, but because we can witness everything it does to the universe around it. For many years, astronomers imagined black holes as cosmic vacuum cleaners. Anything that wandered too close would inevitably disappear. Stars, gas, dust, even light itself. While this image contains an element of truth, it overlooks a remarkable paradox. Some of the brightest objects in the universe are powered not by stars, but by black holes. The black hole itself emits no light. Instead, the brilliance comes from matter just outside the event horizon. Gravity pulls enormous quantities of gas toward the center of NGC 1275. But this material does not plunge directly inward. Like water spiraling into a drain, it carries angular momentum. Unable to fall straight into the black hole, the gas begins orbiting at extraordinary speeds. Over time, these swirling streams flatten into a vast rotating structure known as an accretion disk. Here, the laws of physics become almost unimaginably extreme. Particles race around the black hole at significant fractions of the speed of light. They collide continuously. Friction converts orbital motion into heat. Temperatures soar into the millions of degrees. Atoms become completely ionized. The disk transforms into a blazing sea of plasma brighter than entire galaxies. The closer material approaches the event horizon, the faster it moves. Gravity stretches space and time. Magnetic fields twist into increasingly complex shapes. Matter spirals inward through a violent dance of turbulence, radiation, and magnetic forces. Yet despite gravity's relentless pull, not everything crosses the point of no return. One of the greatest mysteries in astrophysics occurs just above the black hole's poles. There, magnetic fields become so intensely concentrated that they channel part of the inflowing plasma away from the disk. Instead of falling inward, the material is accelerated outward. The result is one of nature's most spectacular phenomena: relativistic jets. These enormous beams of charged particles erupt from opposite sides of the black hole, traveling at velocities approaching the speed of light. They remain astonishingly narrow despite extending for tens, hundreds, and sometimes even millions of light years. No human-made particle accelerator comes remotely close to matching their power. Every second, these jets transport enormous amounts of energy into the surrounding universe. Imagine aiming two giant fire hoses upward and downward from the center of a spinning whirlpool. Now replace water with plasma. Replace the whirlpool with a black hole. And increase the scale until each jet stretches farther than an entire galaxy. That image begins to capture the magnitude of what is happening inside the Perseus Cluster. As these relativistic jets burst outward, they do not travel through empty space. They collide with the immense ocean of hot plasma filling the galaxy cluster. This collision changes everything. Rather than passing through unnoticed, the jets push enormous quantities of plasma aside. Over millions of years, they carve out gigantic cavities inside the surrounding gas. Astronomers discovered these structures through observations made by NASA's Chandra X-ray Observatory. Against the brilliant X-ray glow of the cluster appeared mysterious dark regions, vast bubbles where the surrounding hot plasma had been displaced. These are not bubbles in the familiar sense. They contain extremely energetic particles, tangled magnetic fields, and lower density plasma. Each cavity is so enormous that it dwarfs entire galaxies. Some measure tens of thousands of light years across. If one of these bubbles were placed over the Milky Way, it would engulf a substantial portion of our galaxy. But the bubbles themselves are only part of the story. The truly fascinating phenomenon occurs as they expand. Think about inflating a balloon beneath the surface of a lake. As the balloon grows larger, it pushes water outward in every direction. Ripples spread across the surface. Pressure waves move through the surrounding liquid. The same principle operates inside the Perseus cluster. Only instead of water, the surrounding medium is plasma, and instead of a child's balloon, the expanding cavity is larger than an entire galaxy. Every episode of jet activity inflates new plasma bubbles. Every expanding bubble compresses the surrounding gas. Those compressions generate immense pressure waves that travel outward through the cluster. Although astronomers often compare them to sound waves, they exist on scales unlike anything humans encounter in everyday life. The wavelength of each pressure wave can extend across hundreds of thousands of light years. Imagine a single ocean swell stretching from one side of the Milky Way to the other. Now imagine that wave moving not across water, but through a sea of plasma filling an entire galaxy cluster. The timescales are equally astonishing. On Earth, sound travels from one side of a room in a fraction of a second. Inside Perseus, these cosmic pressure waves require millions of years to complete a single cycle. One pulse may begin long before humanity exists, and continue traveling long after our civilization has disappeared. The black hole is not producing a continuous roar like a jet engine. Instead, it behaves more like an enormous heartbeat. Periods of intense activity, periods of relative calm. Each energetic outburst launches new jets. Each jet inflates fresh plasma bubbles. Each bubble generates another series of pressure waves. Over cosmic time, the cluster becomes filled with overlapping ripples from countless previous eruptions. These oscillations preserve a history of the black hole's activity extending back tens of millions of years. In a sense, the surrounding plasma functions as a cosmic archive. Every ripple contains information. Every cavity records another chapter in the life of the central black hole. By studying these structures, astronomers can reconstruct events that occurred millions of years before human beings ever existed. Remarkably, these waves perform an essential function. Without them, the hot gas filling the Perseus cluster would gradually radiate energy away. As it cooled, gravity would cause the plasma to collapse toward the center. Cold gas would accumulate rapidly. Star formation would accelerate dramatically. The central galaxy would grow far more quickly than observations actually show. Something has been preventing that runaway cooling. For decades, astronomers searched for the missing heat source. The answer appears to be the black hole itself. Every time its jets inject energy into the surrounding plasma, the expanding bubbles distribute that energy throughout the cluster. The pressure waves act as enormous delivery systems, transporting heat across hundreds of thousands of light years. Instead of allowing the gas to cool indefinitely, the black hole repeatedly reheats its environment. This remarkable feedback cycle has transformed modern astrophysics. Black holes are no longer viewed simply as destructive objects consuming everything nearby. They are now understood as regulators of galaxy evolution. By controlling how quickly gas cools, they indirectly determine how many new stars can form. In effect, a single black hole influences the destiny of thousands of billions of stars spread across an entire galaxy cluster. Few discoveries have altered our understanding of cosmic evolution so profoundly. Even more astonishing is the sheer scale involved. The pressure waves generated around the central black hole do not stop after a few light years, or a few thousand. They propagate across distances measured in hundreds of thousands of light years, gradually carrying energy through the vast plasma ocean of Perseus. These are among the largest wave structures ever observed in the universe. Their size challenges human imagination. If Earth vanished tomorrow, the waves would continue moving. If the Milky Way disappeared entirely, the overall structure of the Perseus Cluster would barely notice. Such is the immensity of the environment shaped by this single gravitational engine. And yet, despite all this violence, the black hole itself remains almost perfectly silent. No sound escapes from beyond the event horizon. No roar emerges from its darkness. Everything we have discussed, the jets, the plasma bubbles, the immense pressure waves, originates outside the black hole. The event horizon remains a one-way boundary. Nothing escapes from within. The universe's greatest illusion is that the black hole appears to be speaking. In reality, it is the surrounding plasma responding to the tremendous energy released just beyond the edge of no return. The famous recording created by NASA is therefore not the voice of the black hole itself. It is the voice of an entire galaxy cluster, responding to the presence of one of the universe's most powerful engines. But this realization raises an even deeper question. If these pressure waves resemble sound, can we truly call them sound at all? Or are they something fundamentally different? Waves that obey the same physics, yet exist on scales so immense that human intuition begins to fail. To answer that question, we must look more closely at the nature of sound itself and discover why the universe can remain almost perfectly silent while still carrying vibrations across millions of light years. By now, we know something remarkable. The famous recording released by NASA was not a hoax, nor was it a hidden audio recording captured by a microphone floating beside a black hole. It was based on real astronomical observations, real pressure waves, real physics. Yet one question continues to divide scientists, journalists, and millions of people across the internet. Can we honestly call it sound? At first, the answer seems obvious. Yes. After all, the waves move through plasma, and plasma is a form of matter. But the more closely we examine the physics, the more complicated the answer becomes. To understand why, we must return to one of the most fundamental concepts in nature. What exactly is sound? Every sound you've ever heard shares one essential property. It is a mechanical wave. Unlike light, radio waves, or X-rays, sound cannot exist by itself. It always requires something physical to carry it. When a guitar string vibrates, it pushes against nearby air molecules. Those molecules collide with neighboring molecules. The disturbance spreads outward. Eventually, tiny pressure fluctuations reach your ears. Your eardrums vibrate. Your brain interprets those vibrations as music. The same principle explains thunder, ocean waves crashing against cliffs, birdsong at sunrise, even your own heartbeat. Every sound is simply a pattern of compressions and rarefactions moving through matter. Without matter, there is nothing to compress, nothing to expand, nothing to transmit the wave. That is why astronauts cannot hear each other shouting outside their spacecraft. Between them lies an almost perfect vacuum. No air, no water, no solid material, only emptiness. Their voices simply cannot travel. This scientific fact has been confirmed countless times. It remains one of the defining characteristics of outer space. And yet, the Perseus Galaxy Cluster seems to challenge this idea. If pressure waves are moving through plasma, doesn't that mean sound really exists there? The answer is yes and no. The key lies in understanding the environment itself. Most people imagine outer space as completely empty. In reality, the universe is filled with matter, just not very much of it. Inside Earth's atmosphere, billions upon billions of molecules surround every cubic centimeter of air. The molecules constantly collide. Pressure waves move efficiently. That is why conversations, music, and thunder travel so easily around us. Inside the Perseus Cluster, the situation is dramatically different. The plasma is extraordinarily diffuse. Only a handful of particles occupy each cubic centimeter. Compared with Earth, it is almost unimaginably empty. Yet, almost empty is not the same as completely empty. Those particles still interact. They still exchange energy. They still respond to pressure. Over enormous distances, they are capable of transmitting mechanical disturbances. The physics governing these waves is fundamentally the same as the physics of sound on Earth. Both involve pressure variations traveling through matter. Both transport energy without permanently transporting the material itself. Both obey the same basic principles of wave mechanics. The difference is one of scale. On Earth, sound waves move through dense air over distances measured in meters. In Perseus, pressure waves travel through incredibly thin plasma across hundreds of thousands of light years. The medium is different. The environment is different. The timescale is different. But the underlying physics remains closely related. This distinction explains why astronomers often use the phrase pressure waves rather than simply saying sound. The term is more precise. It avoids confusion. It reminds us that these waves exist under conditions completely unlike anything found on Earth. Understanding this difference also helps clarify another common misconception. Many people confuse sound with electromagnetic radiation. The two are fundamentally different phenomena. Light from the sun reaches Earth across the vacuum of space because light is an electromagnetic wave. It consists of oscillating electric and magnetic fields. It does not require air. It does not require gas. It does not require any material medium whatsoever. Sound behaves differently. It cannot travel through pure emptiness. If every particle disappeared from a region of space, every sound wave would disappear with them. Only light would continue its journey. This distinction is one of the foundations of modern physics. Ironically, both types of waves can carry information. Astronomers have spent centuries studying the universe by collecting electromagnetic waves. Visible light, infrared radiation, radio signals, ultraviolet light, X-rays, gamma rays. Each reveals a different aspect of cosmic reality. The famous Perseus recording represents something new. Instead of observing electromagnetic radiation directly, scientists analyzed how matter itself responds to the energy released by a black hole. They transformed those responses into sound. This process is known as sonification. The word may sound unfamiliar, but the concept is surprisingly common. Every day, computers convert invisible digital information into sounds we immediately understand. A heart monitor transforms electrical activity into rhythmic beeps. A Geiger counter converts radioactive particles into clicking sounds. Parking sensors translate distance measurements into warning tones. Even your smartphone creates audio alerts from streams of electronic data. None of these sounds exist naturally inside the data itself. Instead, they are carefully designed translations that allow humans to recognize patterns more quickly. Astronomers use exactly the same approach. The universe generates enormous quantities of information beyond the reach of our senses. Human eyes cannot detect X-rays. We cannot perceive radio waves. Gamma rays pass unnoticed through our vision. Gravitational waves ripple through Earth without producing audible noise. Yet all of these phenomena contain valuable information. By converting them into images, colors, or sound, scientists expand the range of human perception. The Perseus recording belongs to this growing field of scientific visualization. Or perhaps more accurately, scientific listening. NASA did not invent the black hole's activity. The pressure waves already existed. The observatory measured them. Researchers simply shifted frequencies upward by roughly 57 octaves, bringing them into the narrow range that human ears can detect. Imagine slowing down the wings of a hummingbird until every movement becomes visible, or speeding up the growth of a flower so it blooms within seconds. Nothing about the underlying event has changed. Only the timescale has. Sonification works in much the same way. It translates information into a form compatible with human biology. That translation is both powerful and sometimes misunderstood. One of the most common claims circulating online is that NASA recorded the actual scream of a black hole. This description is dramatic. It is also inaccurate. Black holes do not produce screams. The event horizon itself remains silent. Everything heard in the famous recording originates from pressure waves moving through the surrounding plasma, not from sound escaping the black hole. Another misconception is that NASA somehow discovered ordinary sound traveling through the vacuum of space. Again, this is incorrect. The recording comes from one of the very few known environments where sufficient matter exists to support pressure waves over enormous distances. It does not overturn the well-established principle that ordinary interplanetary space is effectively silent. Perhaps the most persistent misunderstanding is the belief that the recording is entirely artificial. Some critics dismiss it as computer-generated fiction. Others compare it to movie sound effects. Neither interpretation reflects reality. The audio is not fabricated, nor is it a literal recording. It occupies a fascinating middle ground. The scientific data are authentic. The frequencies are authentic. The patterns are authentic. What changes is the scale. Just as astronomers assign visible colors to invisible infrared observations, they assign audible frequencies to inaudible pressure oscillations. The goal is not deception. The goal is accessibility. In fact, sonification has become increasingly important for another reason. Humans are remarkably skilled at recognizing patterns through hearing. Musicians can detect tiny differences in pitch. Doctors recognize abnormal heart rhythms almost instantly. Engineers identify failing machinery by subtle changes in sound. Our auditory system evolved to notice complex patterns that sometimes remain hidden in visual data. By listening to astronomical information, researchers occasionally discover relationships that might otherwise be overlooked. The universe is not only something we observe. Increasingly, it is something we can experience through multiple senses. The Perseus recording represents a glimpse of that future. A future in which data become immersive, where distant galaxies are not only photographed but also heard, where invisible phenomena become tangible, where technology extends the limits of human perception in ways previous generations could scarcely imagine. Yet one mystery still remains unanswered. If these pressure waves carry enormous amounts of energy, what role do they play inside the galaxy cluster itself? Are they simply fascinating byproducts of a supermassive black hole, or do they actively shape the evolution of entire galaxies? As astronomers continued studying Perseus, they uncovered a remarkable answer. The so-called sound of the black hole was never merely an acoustic curiosity. It turned out to be evidence of one of the universe's most important feedback systems, one capable of controlling the birth of stars, regulating the growth of galaxies, and maintaining the delicate balance of an entire cosmic ecosystem. The waves were not just telling us that the black hole was active. They were revealing why the universe around it looks the way it does. When millions of people first listened to NASA's famous black hole recording, their reactions were surprisingly similar. Some described it as unsettling. Others called it haunting. Many compared it to the soundtrack of a horror film. A few even admitted they stopped the recording before it ended. The strange part was that almost everyone knew they were listening to scientific data. There was no monster, no supernatural force, no hidden message, just pressure waves converted into sound. Yet the emotional response remained remarkably powerful. Why? Why would a simple scientific translation trigger such a deep sense of unease? The answer lies not inside the black hole, but inside the human brain. To understand this reaction, we must first examine the sound itself. One of the most fascinating characteristics of the Perseus signal is its incredibly low frequency. In its original form, the pressure wave is far below the range of human hearing. Its oscillation is so slow that a single cycle takes millions of years. No ear, human or otherwise, could ever detect it naturally. NASA solved this problem by increasing the frequency approximately 57 to 58 octaves. That enormous shift compressed millions of years into just a few seconds of audio. Even after this extraordinary transformation, however, the resulting sound remained extremely deep. It occupies the lowest regions of human hearing. If the original wave could somehow be compared to a musical note, it would correspond roughly to a B-flat, so unimaginably low that it lies dozens of octaves beneath the keys of a concert piano. For comparison, the lowest note on a standard piano is A0, vibrating at just 27.5 hertz. The deepest pipes in a cathedral organ descend only slightly lower. The Perseus pressure wave begins far beyond even those limits. Only through massive frequency scaling does it enter a range our ears can perceive. As a result, what we hear is not a melody. It is not a rhythm. It is a slow, heavy vibration that seems to emerge from somewhere beneath ordinary hearing. Humans have evolved to respond very differently to low frequencies than to high ones. A bird singing outside your window often produces frequencies between 2 and 8,000 hertz. Those sounds usually feel light, bright, comforting. By contrast, deep bass frequencies affect us in far more physical ways. Instead of simply hearing them, we often feel them. Anyone who has stood near a massive church organ, an earthquake simulator, or a powerful subwoofer knows this sensation. The chest vibrates. The floor seems to tremble. The body reacts even before the mind consciously identifies the sound. This response has deep evolutionary roots. Throughout human history, many of nature's largest and most dangerous events produced low-frequency vibrations. Thunder rolling across distant mountains, avalanches, volcanic eruptions, earthquakes, the footsteps of enormous animals. Before our ancestors could clearly see these threats, they often sensed their approach through vibration. The nervous system gradually evolved to treat deep, slow sounds as potential warnings. Modern neuroscience suggests that very low frequencies activate brain regions associated with attention, vigilance, and emotional processing more strongly than many higher frequencies. This does not mean every bass sound is frightening. Music proves otherwise. A cello, a double bass, a choir singing deep harmonies. These often evoke beauty and warmth. Context matters. But when low frequencies become unusually slow, irregular, or unfamiliar, our brains struggle to identify their source. Uncertainty itself becomes part of the emotional experience. The Perseus recording contains exactly this combination. It is extraordinarily low. It lacks a recognizable rhythm. It does not resemble any natural sound from everyday life. Your brain instinctively asks a simple question: what am I listening to? When no familiar answer appears, imagination fills the gap. Psychologists have long studied this phenomenon. Humans are exceptionally skilled at recognizing patterns. We constantly search for meaning, even when none exists. We see faces in clouds, animals in rock formations, human figures in the shadows. This tendency, known as pareidolia, extends beyond vision. It also affects hearing. A random arrangement of frequencies can seem like whispers. Static may resemble distant voices. Wind through trees sometimes sounds like faint conversations. The Perseus recording invites a similar response. Many listeners describe it as breathing. Others hear groaning metal. Some imagine a giant creature sleeping beneath the stars. None of these interpretations exist within the data itself. They arise entirely from the remarkable pattern recognition abilities of the human brain. Hollywood has unintentionally reinforced these associations. For decades, filmmakers have used extremely low-frequency drones to create suspense. Long before a monster appears on screen, the soundtrack begins changing. Deep bass notes slowly emerge. Almost imperceptible vibrations build beneath the music. The audience becomes uneasy without fully understanding why. Composers employ these techniques because they reliably influence emotional expectation. When NASA released the Perseus sonification, millions of people unconsciously connected it to those cinematic experiences. The recording already resembled the language of modern horror films. The title only intensified the effect. The sound of a black hole. Those 5 words immediately activate powerful mental imagery: darkness, gravity, the unknown. Even before pressing play, listeners expect something terrifying. Psychologists call this expectation bias. Our interpretation of sensory information depends partly upon what we anticipate beforehand. Consider 2 identical sounds. If one is labeled forest ambience, many listeners describe it as peaceful. If the other is labeled abandoned factory, the same recording suddenly feels ominous. The sound itself never changed. Only the context did. NASA's recording demonstrates this principle beautifully. Had the identical audio been introduced simply as pressure wave data from hot plasma, far fewer people might have found it frightening. Instead, the association with black holes transformed a scientific dataset into something emotionally charged. There is another reason the recording feels unusual. It unfolds across timescales completely foreign to human experience. Almost every sound surrounding us changes rapidly. Speech consists of dozens of syllables every few seconds. Birdsong fluctuates constantly. Ocean waves rise and fall rhythmically. Even thunder usually lasts only moments. The Perseus recording feels different because it originates from a process whose natural rhythm spans millions of years. Even after acceleration, traces of that immense slowness remain. The sound seems ancient, patient, indifferent. It carries none of the urgency associated with living creatures. Instead, it resembles something operating on a timescale entirely separate from human existence. That realization alone can evoke profound emotional responses. It reminds us how small our lives truly are. A single pressure wave inside the Perseus cluster may outlast the entire history of human civilization. Empires rise and fall. Species evolve. Continents drift. Meanwhile, one immense oscillation continues quietly, traveling through the plasma between distant galaxies. There is something deeply humbling about that perspective. And yet, science tells a calmer story than our emotions often suggest. The famous recording does not represent pain. It is not evidence that space is somehow alive. The black hole is not screaming. It is not calling. It is not expressing emotion. The data simply reveal the physical consequences of gravity interacting with hot plasma over unimaginable distances. The pressure waves obey the same mathematical equations governing sound waves on Earth. Their mystery comes not from supernatural origins, but from extraordinary scale. This distinction is important. Emotion is not the enemy of science. In fact, curiosity often begins with emotion. Wonder, awe, even fear. These feelings motivate exploration. They inspire questions. The danger comes only when emotion replaces evidence. Throughout history, people have interpreted eclipses as omens, comets as divine warnings, and earthquakes as acts of supernatural anger. Science gradually revealed natural explanations without diminishing the beauty or power of those events. The Perseus recording belongs to that same tradition. The more we understand it, the more extraordinary it becomes. Not because it confirms ancient fears, but because it demonstrates something even more remarkable. The universe can produce phenomena far stranger than fiction while remaining entirely consistent with the laws of physics. Perhaps that is the greatest lesson hidden within NASA's haunting recording. Reality does not need embellishment. A supermassive black hole launching relativistic jets, inflating plasma bubbles larger than galaxies, creating pressure waves that travel for millions of years, and allowing humanity, through mathematics and technology, to experience those waves as sound, is already one of the most astonishing stories science has ever uncovered. And yet, despite everything we have learned, one essential question still remains. If these enormous pressure waves carry energy throughout the Perseus cluster, what purpose do they actually serve? Are they merely fascinating echoes of a distant black hole, or are they performing a far more important task? One that helps determine how galaxies grow, how stars are born, and how the universe itself evolves. The answer reveals that these haunting vibrations are much more than an eerie sound. They are the heartbeat of one of the cosmos's greatest balancing mechanisms. By now, the famous recording from the Perseus Galaxy Cluster has revealed something remarkable. It is not the voice of a black hole. It is not proof that space suddenly contains ordinary sound. Instead, it is evidence of something far more profound. It reveals that a supermassive black hole is not simply consuming matter. It is actively shaping the universe around it. For decades, astronomers viewed black holes primarily as cosmic endpoints. Stars collapsed. Matter disappeared. Gravity won. The story seemed simple. Black holes destroyed. Galaxies created. The two processes appeared almost independent. Then observations from Chandra, Hubble, XMM Newton, ALMA, and other observatories began telling a very different story. The giant pressure waves spreading through the Perseus cluster were not random. They were performing work. Invisible work. Work that influenced the evolution of galaxies themselves. This discovery transformed one of the central ideas of modern astrophysics. Today, astronomers describe this process using a term that appears repeatedly throughout scientific literature: AGN feedback. AGN stands for active galactic nucleus, the extremely energetic region surrounding a supermassive black hole that is actively feeding on matter. Feedback refers to a self-regulating process. Instead of allowing unlimited growth, the black hole continually influences the very environment supplying its fuel. In simple terms, the black hole helps control its own food supply. Imagine heating water in a pot. As the water grows hotter, steam rises. The escaping steam reduces the amount of liquid available to continue boiling. The system naturally regulates itself. A similar balance appears to exist inside many galaxies. As gas falls toward the central black hole, enormous amounts of energy are released. That energy does not remain trapped near the event horizon. Through relativistic jets, radiation, expanding plasma bubbles, and pressure waves, it spreads outward into the surrounding environment. The black hole returns part of the energy it receives. That returned energy changes everything. Before astronomers understood AGN feedback, computer simulations of galaxy formation produced a serious problem. The largest galaxies became far too massive. Cold gas accumulated continuously. Stars formed at extraordinary rates. Galaxies kept growing long after observations suggested they should have slowed down. Something essential was missing. Theoretical models predicted galaxies that simply did not exist. Then researchers began including feedback from supermassive black holes. Almost immediately, the simulations changed. The galaxies stopped growing uncontrollably. Star formation slowed. The predicted universe suddenly looked much more like the one astronomers actually observed. The missing ingredient had been there all along. The black holes were not passive. They were regulating cosmic evolution. The Perseus cluster provides one of the clearest examples of this remarkable process. Inside the cluster lies an enormous reservoir of superheated plasma. Although this gas reaches temperatures of tens of millions of degrees, it continuously radiates energy into space through X-rays. Over time, that radiation should cool the gas. As cooling progresses, gravity should pull increasing amounts of material toward the cluster's center. Eventually, enormous clouds of cold gas should collapse, creating vast numbers of new stars. Astronomers once expected exactly this outcome. Yet observations revealed something puzzling. The gas remained much hotter than expected. Star formation occurred at only a fraction of the predicted rate. Where was the missing heat coming from? The answer surrounded the black hole itself. Every time the central AGN became active, relativistic jets carved enormous cavities into the surrounding plasma. As those cavities expanded, they generated powerful pressure waves. Those waves transported energy outward through the cluster. Over millions of years, the accumulated heating nearly balanced the energy being lost through X-ray radiation. Instead of cooling indefinitely, the plasma remained remarkably stable. The black hole had become a cosmic thermostat. This idea seems almost paradoxical. Black holes are famous because nothing escapes from inside their event horizons. Yet the regions immediately outside those horizons rank among the most energetic environments in the observable universe. The event horizon itself remains silent, but everything surrounding it can dramatically influence the cosmos. In Perseus, this influence extends across hundreds of thousands of light years. One invisible object affects the future of thousands of galaxies. Even more astonishingly, this process determines how many stars will ever exist. Every star begins as a collapsing cloud of cold gas. If the surrounding gas remains too hot, gravity struggles to compress it. Star formation slows dramatically. By heating the intracluster medium, the black hole indirectly controls whether future generations of stars are born. In other words, the famous pressure waves are not merely echoes traveling through plasma. They are part of the mechanism governing stellar birth itself. Without AGN feedback, many giant galaxies might contain several times more stars than they do today. The night sky of the universe would look fundamentally different. This realization has reshaped modern cosmology. Galaxies are no longer viewed as isolated islands evolving independently. Instead, they are dynamic systems linked to the activity of their central black holes. The relationship works both ways. Galaxies feed black holes. Black holes regulate galaxies. Over billions of years, both evolved together. Astronomers call this coevolution. Evidence for this partnership appears almost everywhere scientists look. The mass of a galaxy's central black hole closely correlates with the properties of its stellar bulge. Larger galaxies generally host larger black holes. The relationship is far too consistent to be a coincidence. Some invisible process has synchronized their growth across cosmic time. AGN feedback appears to be one of the strongest candidates. The Perseus cluster allows scientists to observe this process almost directly. The giant cavities reveal where energy entered the plasma. The surrounding pressure waves show how that energy spread. The X-ray observations measure the temperature of the gas. Together, they tell a coherent story of energy flowing from the central black hole into the entire cluster. No single telescope could have uncovered this story alone. Modern astronomy depends upon multi-wavelength observation. Every region of the electromagnetic spectrum reveals different physical processes. Visible light telescopes show stars and galaxies. Radio telescopes detect relativistic jets and magnetic fields. Infrared observatories reveal cooler dust hidden inside galaxies. Ultraviolet instruments trace energetic young stars. X-ray telescopes expose the superheated plasma surrounding black holes. Gamma-ray observatories capture the universe's most energetic explosions. Each wavelength contributes another chapter to the story. Imagine trying to understand a symphony while hearing only the violins. The music would seem incomplete. Only by listening to every instrument together does the full composition emerge. The universe behaves in much the same way. Each wavelength reveals only one layer of reality. Together, they create a far richer understanding. The Perseus recording itself represents yet another extension of this philosophy. Astronomers did not merely observe the cluster. They translated one aspect of its physical behavior into sound. In doing so, they demonstrated that scientific understanding does not depend upon vision alone. Data can become images. Data can become colors. Data can become sound. Every transformation provides another way for human minds to recognize patterns hidden within nature. This broader approach has become one of the defining features of 21st century astronomy. Future observatories will collect more information than any generation before them. Artificial intelligence will help identify subtle relationships invisible to human observers. Advanced simulations will recreate entire galaxy clusters across billions of years. Gravitational wave detectors will add yet another window into cosmic evolution. Each new technique expands our ability to understand black holes, not simply as isolated objects, but as central players in the history of the universe. Perhaps that is the greatest lesson hidden within NASA's famous recording. The pressure waves are not important because they produce an eerie sound. They matter because they reveal an invisible conversation taking place across millions of light years. A conversation between gravity and plasma, between destruction and creation, between collapse and renewal. The black hole consumes matter, yet prevents even greater amounts of matter from collapsing into stars. It destroys locally while preserving balance globally. Nature often works through such paradoxes. The most violent objects sometimes create stability. The darkest regions sometimes illuminate the deepest truths. The smallest central engine can influence structures millions of times larger than itself. The Perseus Cluster reminds us that nothing in the universe exists in complete isolation. Every galaxy responds to its environment. Every black hole reshapes the space around it. Every pressure wave carries information across unimaginable distances. What once appeared to be a haunting cosmic sound has become something far more meaningful. It is evidence that the universe behaves as an interconnected system, where gravity, energy, matter, and time continuously influence one another across scales almost beyond human comprehension. And yet, despite everything this remarkable discovery has taught us, it also points toward an exciting future. If translating invisible pressure waves into sound revealed so much about one distant galaxy cluster, what other hidden voices might still be waiting inside the universe? As new telescopes, gravitational wave observatories, and next-generation space missions begin listening to the cosmos in entirely new ways, humanity may soon discover that we have only begun to hear the first faint notes of a much greater cosmic symphony. When NASA released the sonification of the Perseus Galaxy Cluster, many people assumed they were witnessing a fascinating curiosity, a clever way to make astronomy more engaging, a scientific novelty, an unusual audio experiment. But for astronomers, it represented something much larger. It hinted at the future of how humanity may one day explore the universe. For nearly 400 years, astronomy has been dominated by one sense: vision. From Galileo's first telescope to the James Webb Space Telescope, we have learned about the cosmos primarily by collecting light. Visible light, infrared, ultraviolet, radio waves, X-rays, gamma rays. Every new telescope expanded the range of electromagnetic radiation we could observe. Each new wavelength revealed another hidden layer of reality. But modern astronomy is entering a new era. Instead of relying only on images, scientists are beginning to analyze the universe in entirely different ways. Some of those methods are visual, some involve mathematics, and increasingly, some involve sound. This does not mean the universe is suddenly becoming audible. Rather, it reflects a growing recognition that the human brain can often detect patterns more effectively through multiple senses working together. Sonification has become an increasingly valuable scientific tool. Large astronomical surveys generate enormous amounts of data every single day. Modern observatories collect far more information than any individual researcher could examine visually. Millions of galaxies, billions of stars, endless streams of numerical measurements. Some patterns hide inside graphs. Others hide within statistical relationships. Some may reveal themselves more clearly when translated into sound. Researchers have already demonstrated that subtle variations in astronomical signals sometimes become easier to recognize through careful sonification. Instead of replacing traditional analysis, listening complements it. The ear becomes another scientific instrument, one capable of detecting rhythm, repetition, irregularity, and change. The Perseus recording belongs to this growing movement. It reminds us that data need not remain trapped inside spreadsheets. They can become experiences. Experiences that communicate science in ways both researchers and the public can appreciate. Yet the future extends far beyond pressure waves inside galaxy clusters. Perhaps the greatest revolution in modern astronomy began not with light, but with gravity itself. For over a century, Albert Einstein's general theory of relativity predicted something extraordinary. When extremely massive objects accelerate, they should disturb the very fabric of space-time. These disturbances travel outward at the speed of light. Einstein called them gravitational waves. Unlike sound waves, gravitational waves do not require air, plasma, or any material medium. Unlike electromagnetic waves, they are not oscillations of electric and magnetic fields. Instead, they are tiny ripples in space and time itself. For decades, many scientists doubted they could ever be detected. The distortions predicted by Einstein were unimaginably small. Even the collision of two black holes billions of light years away would change the length of Earth by less than the width of an atomic nucleus. Detecting such a signal seemed almost impossible. Then, in September 2015, everything changed. The Laser Interferometer Gravitational Wave Observatory, better known as LIGO, detected gravitational waves for the first time in human history. Two black holes had collided more than 1 billion light-years from Earth. The resulting ripple traveled across the universe. After more than 1 billion years of uninterrupted motion, it passed through our planet. LIGO measured it. For the first time, humanity had not merely seen the universe. We had detected its changing geometry. One of the most fascinating aspects of gravitational wave astronomy is that these signals naturally resemble sound, not because they travel through air, but because they consist of changing frequencies over time. Scientists often convert these measurements directly into audio. The famous chirp produced by merging black holes is perhaps the best-known example. As the black holes spiral toward one another, the frequency rises rapidly. The sound climbs higher and higher until the final collision. Then, silence. Unlike the Perseus recording, very little frequency shifting is required. Many gravitational wave signals already fall surprisingly close to the range of human hearing. Listening to them becomes both scientifically useful and intuitively meaningful. LIGO is no longer alone. Across Europe, the Virgo Observatory works alongside LIGO, helping astronomers locate gravitational wave sources with far greater precision. Additional detectors continue expanding this global network. Every new instrument increases humanity's ability to monitor invisible events occurring across the universe. Together, they have transformed gravitational wave astronomy from an experimental idea into one of the fastest-growing fields in modern science. Yet even these remarkable observatories represent only the beginning. Future missions aim to explore an entirely different range of gravitational waves. One of the most ambitious is LISA, the Laser Interferometer Space Antenna. Unlike ground-based observatories, LISA will operate in space. 3 spacecraft will fly millions of kilometers apart, forming an enormous triangular observatory orbiting the Sun. Instead of detecting the rapid mergers observed by LIGO, LISA will listen for much slower gravitational waves. Supermassive black holes gradually spiraling together, compact binary systems orbiting for millions of years, perhaps even signals dating back to the earliest moments after the Big Bang. These frequencies are far too low for detectors on Earth. Only a space-based observatory can observe them. When LISA begins operating, humanity's gravitational hearing will expand dramatically. It will resemble adding an entirely new octave to an already remarkable cosmic symphony. Another revolution is unfolding simultaneously: artificial intelligence. Modern observatories produce staggering volumes of information. Future telescopes will generate far more data than human researchers could manually examine. Machine learning systems are becoming essential partners in scientific discovery. AI can rapidly identify subtle correlations hidden inside enormous datasets. It can recognize repeating patterns, classify signals, detect anomalies, separate genuine astronomical events from background noise. Increasingly, researchers are combining AI with sonification techniques. Instead of asking computers only to analyze numbers, scientists are teaching them to recognize acoustic patterns hidden within transformed data. Some systems even generate interactive soundscapes, allowing researchers to explore astronomical observations almost as musicians explore complex compositions. The collaboration between artificial intelligence and human intuition may become one of astronomy's most powerful tools. Machines excel at processing enormous quantities of information. Humans remain remarkably skilled at recognizing unexpected relationships. Together, they form a partnership capable of exploring the universe in entirely new ways. This evolution reflects a broader truth. Astronomy has never been limited to what human senses naturally perceive. Every telescope extends our vision. Every detector expands our awareness. Every new technology increases the portion of reality we can investigate. In that sense, sonification is not merely about hearing. It is about translation. The universe continually produces information. Science continually develops better ways to understand it. Perhaps one day, humanity will routinely explore astronomical data through immersive environments combining images, sound, touch, and advanced visualization. Instead of simply looking at galaxies, researchers may navigate through multi-dimensional datasets where every wavelength, every particle, every gravitational signal contributes to a rich sensory experience. Future students may not merely study black holes. They may interact with them. Not physically, of course, but through sophisticated scientific representations that reveal relationships impossible to perceive today. This raises an irresistible question. Could we someday hear the entire universe? The answer depends on what we mean by hear. If we imagine placing our ears into space and listening to ordinary sound, probably not. Most of the universe remains far too empty for traditional sound waves to travel. Silence will continue to dominate the cosmic vacuum. But if hearing means translating every measurable phenomenon into forms accessible to human perception, then the answer becomes far more intriguing. We may eventually experience the universe through a continuously expanding orchestra of scientific information. Pressure waves from galaxy clusters, gravitational waves from colliding black holes, radio emissions from pulsars, magnetic oscillations surrounding distant planets, perhaps signals not yet even discovered. Each would represent another instrument in an ever-growing cosmic symphony. Not because the universe literally performs music, but because mathematics allows us to transform hidden patterns into experiences our minds can understand. The famous recording from the Perseus Galaxy Cluster may therefore represent far more than an isolated scientific achievement. It may be remembered as one of the first moments when humanity truly began listening to the cosmos. Not with microphones, not with ears alone, but with technology, imagination, mathematics, and centuries of accumulated scientific knowledge. The universe has always been speaking through gravity, light, plasma, and space-time. Only now are we beginning to learn its many languages. And perhaps the greatest discovery still lies ahead. The next extraordinary signal may not arrive as a spectacular photograph. It may not appear as a graph or a table. Instead, the next great breakthrough in astronomy may begin with something surprisingly simple, a sound no human being has ever heard before. At the beginning of this journey, we asked a simple question. Did NASA really record the sound of a black hole? It was a question that spread rapidly across the internet. It inspired headlines, videos, debates, wonder, and sometimes misunderstanding. After traveling from the silent vacuum of space to the fiery heart of the Perseus Galaxy Cluster, through plasma, relativistic jets, pressure waves, sonification, and gravitational physics, the answer has become both simpler and far more extraordinary. NASA did not discover that black holes make ordinary sounds. The real discovery was something much deeper. Humanity discovered a new way to observe the invisible. For centuries, astronomy depended almost entirely on light. Every telescope, no matter how sophisticated, ultimately collected photons. Some gathered visible light. Others observed radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays. Each expanded our understanding of the universe. Yet all belong to the same family of electromagnetic radiation. The Perseus recording represents a different philosophy. Instead of asking only what the universe looks like, scientists asked another question. How does the universe behave? How does energy move? How does matter respond? How does gravity reshape its surroundings over millions of years? The answers were hidden inside pressure waves traveling through an ocean of plasma. Not visible to human eyes, not audible to human ears, yet undeniably real. The famous recording transformed those invisible patterns into something we could experience. Not because the universe suddenly became louder, but because humanity became better at listening. Perhaps that is the most important lesson of all. The recording is not about sound. It is about communication. Not communication in the human sense. The black hole is not sending messages. It has no intention, no consciousness, no voice. Yet every burst of energy from its accretion disk changes the surrounding plasma. Every relativistic jet inflates enormous cavities. Every expanding cavity launches pressure waves. Those waves carry information across hundreds of thousands of light years. They tell astronomers how much energy the black hole released, how often it became active, how efficiently it heated the surrounding gas, how it influenced the evolution of the entire galaxy cluster. In that sense, the black hole communicates continuously with its environment, not through language, not through sound, but through physics. The universe has always communicated this way. Stars reveal their temperatures through color. Galaxies reveal their motions through redshift. Atoms reveal their composition through spectral lines. Gravity reveals itself through orbital motion. Black holes reveal themselves through their influence on everything around them. Nothing in nature remains completely isolated. Every object leaves traces. Every interaction creates consequences. The challenge has never been that the universe refuses to communicate. The challenge has been learning how to interpret its language. Human history is filled with examples of expanding perception. There was a time when bacteria were completely invisible. Then microscopes revealed an entire hidden world. Radio waves passed unnoticed through Earth for billions of years. Then antennas allowed us to detect them. Gravitational waves rippled silently through the cosmos long before Einstein predicted them. A century later, humanity finally learned how to measure them. Each scientific breakthrough follows a similar pattern. Reality remains unchanged. Only our ability to perceive it evolves. The Perseus recording belongs to that long tradition. The pressure waves always existed. The plasma always oscillated. The black hole always influenced its surroundings. Only recently did our technology become sophisticated enough to recognize those patterns and transform them into something our senses could understand. This idea reaches beyond astronomy. Science has always been the art of making the invisible visible. Today, It is increasingly becoming the art of making the invisible perceptible. Invisible magnetic fields become colorful maps. Invisible molecules become three-dimensional models. Invisible gravitational waves become audible chirps. Invisible pressure oscillations become haunting cosmic echoes. None of these representations are illusions. Neither are they literal experiences. They are translations. And translation is one of humanity's greatest intellectual achievements. It allows us to cross boundaries that biology alone could never overcome. Our eyes evolved beneath Earth's atmosphere. Our ears evolved to detect nearby predators and human voices. They were never designed to perceive black holes, or X-rays, or space-time itself. Science extends those natural senses. Every instrument humanity builds becomes another sensory organ. Telescopes expand vision. Spectrometers reveal chemistry. Particle detectors expose invisible radiation. Gravitational wave observatories detect distortions in space-time. Computers transform mathematical patterns into images and sound. Step by step, our perception expands beyond the limits imposed by evolution. This expansion changes more than science. It changes perspective. Standing beneath the night sky, it is easy to imagine ourselves separated from the distant universe. The stars appear fixed, silent, untouchable. Yet everything we have explored tells a different story. The Perseus Cluster may lie approximately 250 million light-years away. But the physical laws operating there are the same laws governing every heartbeat inside your body. Pressure, gravity, energy, motion, matter. The equations never change, only the scale does. That realization is profoundly humbling. The black hole at the center of NGC 1275 possesses a mass hundreds of millions of times greater than our Sun. Its jets stretch across intergalactic space. Its pressure waves require millions of years to complete a single oscillation. Human civilization occupies only a tiny fraction of that timeline. Entire species appear and disappear while one enormous wave continues quietly moving through the plasma. Measured against such scales, individual human lives seem almost impossibly brief. And yet, within those brief lives, an intelligent species evolved on a small rocky planet orbiting an ordinary star. That species asked questions, built telescopes, developed mathematics, launched observatories into space, detected invisible X-rays, mapped giant plasma bubbles, measured ancient pressure waves, converted them into sound, and ultimately understood what they meant. Perhaps that is the true miracle. Not that the universe is vast. The universe has always been vast. Not that black holes are powerful. They have always been powerful. The remarkable achievement is that creatures as small as ourselves can comprehend even a tiny part of that immense reality. Knowledge does not make the universe smaller. It makes wonder larger. The more we learn, the more extraordinary reality becomes. What first appeared to be the frightening scream of a black hole has transformed into something far more elegant. A natural consequence of gravity. A magnificent example of cosmic balance. A demonstration that destruction and creation often coexist. The black hole does not simply consume matter. It regulates galaxies. It controls the temperature of intergalactic plasma. It influences the birth of future stars. Its apparent violence sustains long-term stability. Nature repeatedly teaches this lesson. Processes that seem chaotic often create order. Processes that appear destructive often preserve balance. The universe is rarely as simple as first impressions suggest. Neither is science. Every answer uncovers deeper questions. What other hidden signals remain undiscovered? What new observatories will future generations build? What invisible phenomena are passing through Earth at this very moment, unnoticed only because we have not yet learned how to detect them? History suggests a remarkable possibility. The universe is probably not becoming stranger. We are simply becoming better observers. And perhaps one day, Future scientists will look back on the Perseus recording the way we now look back on Galileo's telescope, not as the final discovery, but as the beginning of an entirely new way of exploring reality. Because in the end, NASA did not teach us that black holes can scream. It taught us something infinitely more profound. The universe is constantly speaking through the language of physics. Gravity, plasma, light, space-time, energy. Our task is not to invent those voices. Our task is to learn how to hear them. So the haunting sound from the Perseus Galaxy Cluster is not the cry of a monster hidden in the darkness. It is not the scream of a black hole trapped beyond its own event horizon. It is something far grander. A slow, majestic pulse traveling through an ocean of plasma. The heartbeat of an entire galaxy cluster, echoing across hundreds of thousands of light years, for tens of millions of years, reminding us that even in a universe that often appears silent, the laws of nature have been telling their story all along. We simply had to learn how to listen.